Hello. In this video, we're going to start taking a more abstract perspective when we talk about linear algebra. Today's discussion is going to be about vector spaces. We actually covered the basics of properties of vectors at the beginning of the semester, so let's briefly review that. If you have two vectors u and v, and we always assume these vectors are in Rn, and a scalar c, we can add the vectors together to get a new vector, and we can also scalar multiply to get another new vector. And from these two basic operations of vector addition and scalar multiplication, we arrive at the concept of a linear combination. So if you combine vectors via scalar multiplication and addition, it produces a new vector for you. So let's write a vector as a linear combination of other vectors. Let's take the vector x, for example. -1, -2, and -2. We want to write x as a linear combination of three other vectors. So u, v, and w. And I've just picked a few vectors here. So if we want to write x as a linear combination of these three vectors, that means we're trying to find scalars a, b, and c so that x is some combination like this, au plus bv plus cw. If we can find a, b, and c, then we found the linear combination. So there's several ways to go about doing this. Let's make a little bit of space on the page and compare the different ways that we think about this. We can think about this as a vector equation. So we are trying to solve for a, b, and c. As vectors, we would write a scalar a times the first vector, plus a scalar b times the second vector, what I had called v from here, plus a scalar times the vector w. And we want to know which combination of them is going to give us x. This is writing it as a vector equation. We could also think about this as a system of equations. Now, instead of having the numbers collected into the vectors, we're going to put them as the coefficients in a system of equations. And then a, b, and c are written out in every line of the system of equations. And we're still trying to solve for a, b, and c. Probably the most efficient way to think about solving this problem is as a matrix equation. This is yet another way to package the same problem, but now we're looking for the vector a, b, c that solves this matrix equation. Even though the role of a, b, and c is that they are scalars in the sense of this linear combination and in the sense of this vector equation, when we write this problem in this manner as a matrix equation, those three scalars embody the vector that makes up the solution to the problem. So take a moment and compare and contrast the different ways of thinking about this problem and ask yourself, well, how would I go about solving this? Well, by now we have a very good method for solving any one of these three variations of this problem. Guess what? It's Gaussian elimination. So we already know how to solve this. The solution for this problem using Gaussian elimination is written right here. I won't go through every step slowly because we've worked problems like this many times, but you take your augmented matrix A followed by the vector that you're trying to express as the linear combination of the other three. And you use the steps, the row operations, to put it into reduced row echelon form. When you finally arrive at reduced row echelon form, then you're able to read off the solution. In this case, it's a is 1, b is -2, and c is -1. Now, what we had originally asked was to describe the vector -1, -2, -2, which appears in the problem here, as a linear combination of three vectors, these three. So this is the solution written out in that perspective. Our vector is 1 times the first vector, -2 times the second vector, -1 times the third vector, and you can see that it works out. So Gaussian elimination is yet again a useful tool. If you want to solve a system of equations, use Gaussian elimination. If you want to find the inverse of a matrix, use Gaussian elimination. If you want to factor a matrix, you can use Gaussian elimination. And here's another variation of that problem. Here we were asked to write one vector as a linear combination of other vectors, and guess what? We also used Gaussian elimination. Before I define a vector space abstractly, let's look at a single example. Okay, our example will be polynomials of degree at most 2. So instead of taking a vector like an arrow in R2 or R3, let's think of having a polynomial of degree at most 2. It could be degree 0, degree 1, or degree 2. And the observation to make here is you can add polynomials and you can scalar multiply polynomials. Let's be more concrete about this. let's take two polynomials. We're going to take polynomial p and polynomial q. Because these are degree 2, or at most degree 2 polynomials, that means you can write them out. P, we're going to say, has coefficients ai, so a naught plus a1x plus a2x squared, where it's okay if one of these a's is 0. And q is going to be b naught plus b1x plus b2x squared. Basic arithmetic tells you how to add polynomials and how to scalar multiply them. This is something you already know how to do. When you add the polynomial p to the polynomial q, what do? Well, you add up the constant terms. A naught gets added to b naught. And you add up the x terms. a1x gets added to b1x. And you add up the terms in front of the quadratic as well. Scalar multiplying a polynomial means scalar multiplying through the whole thing. And when you distribute across the parentheses, you see that all of the coefficients are multiplied through with a c as well. So you can add polynomials and you can scalar multiply them. So the takeaway here is that polynomials of degree at most 2 form a vector space. And they form a vector space because you can take linear combinations of them and produce another of the same object, that is, a polynomial of degree at most 2. Now, it's important to think about the role of the phrase at most in this example, because you can think of some polynomials where you added them together, you might see some cancellation. For example, if I take the polynomial p of x to be 1 plus 7x minus 2x squared, and I take my polynomial q of x to be 2 minus 3x plus 2x squared. These are both degree 2 polynomials, and when I add them together, p of x plus q of x, well, obviously I'm going to get 3 plus 4x, and then the minus 2x squared and the plus 2x squared will cancel. So it's possible that the degree of this polynomial can go down. So as long as I remain within the set of polynomials of degree at most 2, including those of degree 1, like this, or degree 0, which would mean just a constant, then this addition of vectors is remaining in that same set. It's closed under addition. Let's use this example, think about it, and then write down the general definition of a vector space. All right, we're going to need some space to do that. Let me just lay it down. Here's the definition of any vector space. So the vector space is going to be capital V. And V is a set of mathematical objects. Those might be the traditional vectors that we think of in R2 or R3. It might be something like polynomials or anything else. A set with 2 operations. Those operations are vector addition and scalar multiplication. And these operations of addition and scalar multiplication need to satisfy some rules that we call axioms. These axioms hold for all vectors and scalars. Now, we are taking our scalars in this definition still to be real numbers. It's possible that you could state things more generally, but we're going to take as our definition a vector space over the reals. And so it's going to make it what we call a real vector space. And so there are 10 axioms that need to hold. In this, u and v are going to be vectors, even though I'm not denoting them with little hats over them. U and v stand for vectors, and as usual, c is going to stand for a real number. You need to be able to add 2 vectors together and get a new vector. It's closed under vector addition. And you need to be able to scalar multiply a vector and still have a vector in the set V. These are the 2 most important properties: closure under addition and closure under scalar multiplication. And then when you have these operations that are closed, the rest of the items here are rules that they follow. For example, u plus v is equal to v plus u. So this addition is commutative. There are some associative rules. For example, rule 3. You can first add together v plus w, or first add together u plus v, and you're going to get the same vector. We have rules about the 0 vector. Every vector space contains a 0 vector. And it is called the 0 vector because it operates the way that we think of 0 with respect to addition. If you take a number and add 0 to it, you don't change it. If you take a vector and add 0 to it, you don't change it. And every vector needs to have its own additive inverse that we can denote minus u, so that when you add them together, you get the 0 vector. There's another couple of rules dealing with scalar multiplication and how it distributes with respect to addition. And then the last rule is rule 10 here, and that tells us that if we take the real number 1 and we scalar multiply times a vector in our set V, we should get u back. In the context of vectors in Rn, these are quite familiar rules, but these are the defining properties of any vector space.